Hello everyone, here is Afra. Today we are going to solve Cambridge IGCSE Physics Paper 4 Theory Extended. Paper code is 0625 with variant 43. Held on May or June 2021. So let's start from question number 1. Question number 1. Figure 1.1 shows a load suspended from a spring. The value of the spring constant K of the spring is 0.20 Newton per centimeter. The spring reaches the limit of proportionality when the load is 50 Newton. Part A. Calculate the extension of the spring when the load is 3.0 Newton. So in figure 1.1 we can see that there is a load and it is attached with the spring. So here we have to calculate the extension when the load is 3.0 Newton. This load is 3.0 Newton and the spring constant of this spring is 0.20 Newton per centimeter. So we have to calculate the extension x. According to Hooke's law, the extension is directly proportional to the applied load, or load is directly proportional to the extension. I write here F represents the load and x represents the extension. The load is directly proportional to the extension, and to remove this sign of proportionality we write here constant and it is K, where K is spring constant and the value of K will be equal to load per unit extension. So in the question we are given that the load is 3.0 Newton and spring constant is 0.20 Newton per centimeter. Here we have to calculate the extension. So from this formula I separate extension x and it will be equal to load per unit spring constant. So x will be equal to load is 3.0 Newton divided by spring constant is 0.20 Newton per centimeter. So the extension comes to be 15 centimeter. I write here 15 centimeter. Part B. Explain what is meant by the term limit of proportionality of the spring. So this is basically the limit where Hooke's law is obeyed, that extension is directly proportional to the load. So in the Hooke's law, the load is directly proportional to extension and this is only hold in the limit of proportionality where we write F is equal to Kx. So I write here extension of a spring is proportional to load up to the limit of proportionality. After the limit of proportionality, the extension is not proportional to the load. Part C. On figure 1.2, sketch an extension load graph for a spring. Label the limit of proportionality with let L on your graph. So here we can see that in figure 1.2, on the x-axis load is taken and on y-axis extension is taken. We should be very careful because in some graph extension is taken along x-axis and load is taken along y-axis. So here according to Hooke's law we know that load is directly proportional to extension When we increase the load, extension also increases. Both varies directly with each other. So there will be a straight line between extension and load. So I'm going to draw this. And this is basically in the limit of proportionality. So the graph will be a straight line. This curve is basically shows that the load is directly proportional to extension. When I increase the load, extension also increases. When I decrease the load, extension also decreases. And this region is basically the limit of proportionality. After the limit of proportionality, this curve is not a straight but it is curved, which shows that the gradient increases. So it will be just like this. At this point and before this point, extension is directly proportional to load. It means that it is the region of proportionality. After that point, the load is not directly proportional to extension. It's a increasing gradient. It means that in this region, we can say that Hooke's law does not obey. So I label it with L. Moving towards the next part, part D. The load is pulled down a small distance below its equilibrium position to position A, as shown in figure 1.3. The load then moves up and down between position A and position B in figure 1.3. So in the figure 1.3, we can see that there is a spring and two positions are mentioned here, position B and position A. These two positions are actually the extreme position of the spring. So there is also mentioned that the load is pulled down a small distance below its equilibrium position. So this load, first of all, when it is at rest, this position is its equilibrium position. I write here spring at rest. This position is equilibrium position. And when the spring is extended or compressed, it means that it covers a small distance from its equilibrium position, then that position is known as extreme position. The extreme position here is represented with position B and position A. So first of all, we have to know that what is the mean position or equilibrium position of this spring. So this position lies between the position A and B. So I am going to draw this one. This will be at the mid between A and B. So this position is basically the equilibrium position of this spring. No, when the spring is extended, it is at the position A. So when at position A it is extended, it means that the energy stored in the spring is actually elastic energy. So when the spring moves from position O to position A, all the energy is elastic energy. So when the spring is moved from position A to O, then O position is actually equilibrium position. I write here at equilibrium position. The speed of the spring is maximum. V is maximum. And at position B, the speed is 0. And we know that the speed is related with the kinetic energy. Kinetic energy is the energy possessed by a body due to its motion, and kinetic energy is associated with the speed. So I simply write here that kinetic energy here will be maximum, and it is equal to 1 over 2 mv square. But at position B, as the speed is 0, that's why kinetic energy also be equal to 0. So I write here speed is maximum. So at position O, all of the energy is kinetic energy. So in the first question, describe the energy transfer which occur as the load moves from position A to the equilibrium position. So at the position A, all of the energy is elastic energy, because at position A the spring is extended. So here is elastic energy. When this load moves from position A to O, then all of the elastic energy changes into kinetic energy. So I write here the energy transfer will be from elastic energy to kinetic energy. Next part, from the equilibrium position to position B. So going back to the diagram, when this load moves from position O to position B, then what will happen? At position A, the kinetic energy is maximum, and because speed is maximum. So when this load moves at this position, it means that it is compressed, and this is basically due to the height, because it is the equilibrium position, and at this position the load is at maximum height. And we know that from this, that at position B the velocity is 0. It means that kinetic energy is equal to 0. I write here at position B kinetic energy is equal to 0. So when the load moves from equilibrium position to position B, it means that all of the kinetic energy is converted into gravitational potential energy, because the potential energy is associated with height. At the position B, body is at maximum height from the equilibrium position. That's why here will be the gravitational potential energy. So when the load moves from position O to B, the conversion will be from kinetic energy to gravitational potential energy. I write here kinetic energy to gravitational potential energy. Question number 2, part A. Figure 2.1 shows a bookshelf with two groups of books A and B on it. There are 6 books in each group of books. All the books are identical. The mass of each book is 0.52 kg. In figure 2.1, we can see that there are two groups of books, group A and group B. The area of each set of groups is given, and the length, breadth and total height of these books is also given. Part 1. Explain why the pressure exerted on the shelf by the books in group B is less than the pressure exerted on the shelf by the books in group A. Here we have to tell that why the pressure that is exerted by the group B. Pressure exerted by group B is less than the pressure exerted by the books A. So in this figure 2.1, we can see that the area of group B is this. This is the top area, while there is also the area at the bottom, and it will be just like this. Similarly, if we shade the area of group A books, this will be at the top the area is this, and at the bottom the area is just like this. And we know that pressure is defined as force per unit area. In the question, it is given that there are 6 books in each group of books and all the books are identical. It means that force on each book is same. So the force on group A of books and group B of groups are identical. I write here F of A is equal to F of B. Force is same. So if the force is constant, what will be the relation between pressure and area? Pressure is inversely proportional to area. Now we check the area, that which set of books have larger area and which have smaller area. So in figure 2.1 we can see that the group B of the books have larger area as compared to group A. I write here this has large area as compared to this one. So area of group B is greater than area of group A, and the pressure is inversely proportional to area. It means that pressure of B is less than pressure of A. So the pressure that is exerted by the group B of books is less than as compared to the pressure of group A of books. So I write here as pressure is equal to force per area. Force exerted by each group of books is same, and area of group B is greater as compared to area of group A. That's why the pressure of group B is less than the pressure of group A of books. Part 2. Calculate the pressure exerted on the shelf by the books in group A. Here we have to calculate pressure, and we know that pressure is equal to force per unit area. For that we have to calculate the force and area. So first of all we can calculate area for group A. From this figure we know that the area is the product of length and width. Here this 1.3 centimeter, this is basically the length of one book, but there are 6 books in one set. So we have to find out the length of 6 books. I write here area is equal to length multiplied by width, and length for one book is 1.3, and there are total 6 books in each set. So I multiply it with 6, and from this figure we can see that the width is 21 centimeter. So I multiply it with 21 centimeter. But we have to calculate the area in meters. For that, I multiply 1.3 with 10 की power minus 2 to convert centimeter into meters, and then 21 into 10 की power minus 2. This area comes into meter square. Secondly, we also have to calculate force for the calculation of pressure, and force is basically equal to weight. And in the question it is given that mass of each book is 0.52 kg. So we have to calculate the mass of 6 books. For that, I write here that weight for one book. Weight is the product of mass and acceleration due to gravity, where mass is given 0.52 multiplied by 10, and it comes to be 5.2. Secondly, we have to calculate this weight for 6 books. So I multiply it with 6. 6 multiply 5.2. It comes to be 31.2 newtons. So I write here 31.2 divided by area is 1.3 into 10 की power minus 2 multiplied by 6, 21 into 10 की power minus 2. So the pressure comes to be 1900 Pascal. The unit of pressure is Pascal. I write here 1900 Pascal. Part B. A diver dives to a depth below the surface of sea, where the total pressure is 3.0 into 10 की power 5 Pascal. The atmospheric pressure is 1.0 into 10 की power 5 Pascal. The density of sea water is 1030 kg per cubic meter. Calculate the depth of the diver below the surface of sea. So first of all, I consider a sea. Now I consider that the diver is below the surface of sea. So I consider that his position is this. At that position diver lies. And the total pressure will be the sum of atmospheric pressure plus pressure due to the sea water. So the total pressure is given 3.0 into 10 की power 5 Pascal, while the atmospheric pressure is 1.0 into 10 की power 5. So when we have to calculate the pressure due to the sea water, we just write total pressure is equal to atmospheric pressure plus pressure due to sea water. Here we have to calculate the pressure due to sea water. It will be equal to total pressure minus atmospheric pressure. Total pressure is 3.0 into 10 की power 5 minus atmospheric pressure is 1.0 into 10 की power 5. So it comes to be 2.0 into 10 की power 5 Pascal. This is the pressure of sea water. So here we have to calculate the depth of diver below the surface of sea. We have to calculate the depth below the surface of sea. That's why we need the sea water pressure. And we know that pressure is equal to rho GH, where rho is density of sea, G is acceleration due to gravity, and H is depth. So we have to calculate H. It comes to be P over rho G. This is sea water pressure. it comes to be 2.0 into 10 की power 5 divided by density is 1030 multiplied by the acceleration due to gravity is 10 meter per second square. So the depth comes to be 19 meters. I write here depth is equal to 19 meter. Question number 3. A car travels at constant speed v on a horizontal straight road. The driver sees an obstacle on the road ahead. Part A. The distance traveled in the time between the driver seeing the obstruction and applying the brakes is the thinking distance. Explain why the thinking distance is directly proportional to v. So in this part we have to explain that what is the thinking distance and how it varies with speed v. So first of all, if I consider that it's a car and it is moving on the road. The position of car is this. So if I consider that at point there is a obstacle, when the driver driving a car, then he sees a obstacle in front of him. Then what he will do? First of all, he will think that what he has to do, then he applies the brake. The distance between he sees the obstacle and then apply the brake is actually the thinking distance. So if I consider that at this position he applies the brake, so this distance is basically the thinking distance. I write here this distance is thinking distance. Here we have to show that the thinking distance is directly proportional to v. We know that the velocity is equal to distance, which is thinking distance, divided by time. This time is basically the time to think, and this time is completely dependent on the driver and it is independent of anything else, and it is same. It means that its value is constant. It is independent how fast a slow car is moving. So this is thinking time and its value is same. It means that it has constant value. So we can simply say that when the time is constant, then the thinking distance, if I increase the thinking distance, then the speed also increases, and if I decrease the thinking distance, the speed also decreases. We can simply say that the v is directly proportional to distance. So I write here thinking time is constant That's why the thinking distance is directly proportional to v. Part B. When the brakes are applied, the car decelerates uniformly to rest. First of all, it is moving with uniform speed and then its speed becomes equal to 0. It comes to rest. The frictional force applied by the brakes is constant. The distance traveled between the first applying the brakes and car stopping is the braking distance. So here is the definition of braking distance, that this is the distance traveled between the first applying the brakes, when the driver applied the brakes, and then the car stopped. The distance between these two events is basically the braking distance. Explain why the braking distance is proportional to v square. So why this distance is proportional to v square? So first of all, a car is moving at constant speed. Then it has the energy that is stored in it in the form of kinetic energy, because it's moving and kinetic energy is associated with the motion of car. So first of all, I consider that it's a car and it is moving with constant speed. then there will be the kinetic energy associated with this motion, and it is equal to half mv square. So when he see obstacle, then he applies the brake, and after some time car comes to rest. Then some of the energy, that is the kinetic energy, is used to work against the friction, because there is also the friction and car has to stop. That's why some of this kinetic energy is used to do work against friction, so that the car comes to rest. And we can simply say that the kinetic energy is equal to half mv square, and work done is product of force and the distance that car travels. So we know that the mass of car is constant and the force is also constant. So here v square is proportional to d. It means that when we increase the braking distance, then v square also increases. The distance varies with the square of velocity. So I write here kinetic energy of the car is half mv square. This energy will use to do work against friction. And half mv square is equal to F and D. So here mass and force is constant. That's why we can see that the stopping distance is directly proportional to the square of speed, that is v square. Part C. The car is traveling at 22 meter per second. Part 1. The thinking distance is 15 meter. Calculate the time taken to travel the thinking distance. Here we have to calculate the time that the car taken to travel the thinking distance, where speed and distance is given. So using the formula that v is equal to thinking distance over thinking time, here we have to calculate the time. So t will be equal to d over v. Here the thinking distance is 15 meter and speed is 22 meter per second. So the time comes to be 0.68 second. I write here time is equal to 0.68 second. Part 2. The car has a mass of 1400 kg. The time taken for the car to stop after the brakes are applied is 2.1 seconds. So here mass is given and time is given. Calculate the force required to stop the car in this time. It means that first the car is moving at the speed of 22 meter per second, that is given here. Then he stops. It means that the final velocity is equal to 0 while the initial velocity is 22 meter per second and time is also given. We know that impulse I is the product of force and time, and it is also equal to change in momentum delta P, and change in momentum is the product of mass and change in velocity delta V. So here we have to calculate force. That's why I write F cross T is equal to M delta V. So here force comes to be M delta V divided by time T. Mass is given, that is 1400 kg, and change in velocity is 22 because final velocity is equal to 0. Divided by time is given to 2.1 seconds. So the force comes to be 15,000 Newton. I write here force is equal to 15,000 Newton. Question number 4, part A, 1. Define specific latent heat of fusion. So here we have to write the definition of specific latent heat of fusion. If I consider that it's 1 kilogram of solid, one kg of substance that is solid. In order to convert this solid into liquid, energy requires. So the amount of energy that is required to convert 1 kg of solid into liquid is basically the specific latent heat of fusion. So I write here energy required to convert 1 kilogram of solid substance into liquid. So this is basically the specific latent heat of fusion. Part 2. A cup of water contains 250 cubic centimeter of water at temperature 0 degrees C. An identical cup contains 250 cubic centimeter of mixture of ice and water at temperature of 0 degrees C. The temperature of the surrounding air is 20 degrees C. State and explain which cup contains the liquid with lower temperature after 10 minutes. So here we have two cups. This is first cup and this is second one. In the first cup we just have water. So here is just water. And on the second cup we have a mixture of water and ice. Water plus ice. So this will be in first cup will contains only liquid, while the second one contains liquid and solid. Solid is basically ice. So this is liquid and this is solid inside this. Now both of these contains equal value, that is 250 cubic centimeter. And the temperature of both is 0 degrees C. The temperature of surrounding is 20 degrees C. So here we can see that the surrounding temperature is larger as compared to this cup of water and ice. So when the temperature of surrounding is larger as compared to this 0 degrees C, then what will happen? Some energy from the surrounding is transferred into these cups. It means that the temperature of the surrounding is shifted towards the cup. So first consider the first cup. For the first cup we can see that there is a liquid. And when its initial temperature is 0 degrees C and final temperature when heat shift inside this is 20 degrees C. So there will be absorbed the temperature from the outside, and in order to increase the temperature of this, the temperature of water also increases. So I write here when this water gains energy from outside, then its temperature increases. So I write here at 0 degrees C, when it's come at 20 degrees C, then the temperature of this liquid increases. But for second cup, it's a mixture of water and ice, which is solid and liquid. So when this mixture gains energy from outside, then This energy is used to change the phase. That means the energy is used to change the solid into liquid or melting for ice. So I write here, for second cup, there will be no increase in temperature because all the energy is used to convert solid into liquid. As a result, the temperature of this mixture remains low. Temperature does not increase. That's why the temperature increment for the first cup is more as compared to the second. I write here in the statement, the cup containing mixture of ice and water. This cup has lower temperature after 10 minutes when temperature increases up to 20 degrees C. In explanation, I write that the mixture of water and ice will remain at 0 degrees C until all ice melt. So first of all, when we increase the temperature of mixture of water and ice, then ice convert into water. All of the energy is used to change the phase. That's why the temperature of this mixture does not increase. Part B 1. On a hot day, sweat from a person's skin and then evaporates. Explain in terms of molecules how the evaporation of sweat cools the person. We know that the process of evaporation causes cooling. So here, by the process of evaporation, cooling produces. So we know that evaporation is basically the escape of molecules from the surface of liquid. If we consider that it's a cup and it contains liquid, some molecules lie at the surface of this liquid while the some lies inside. So the molecules that lies at the surface of liquid has large energy as compared that lies at the bottom. So the highly energetic molecules escape from the surface of liquid and it causes evaporation. As a result, the temperature of the other liquid decreases. The molecules that is at the bottom, they have low energy. They do not escape from the surface. So there will be the cooling. I write here, in evaporation, first point is that in evaporation, more energetic molecules escape from the surface of liquid. Second is that low energy molecules remains in the liquid because they don't have enough energy to cause evaporation. and the thermal energy is taken from person. By high energy molecules. To escape from liquid surface. Person lost some energy, that's why person cools down. Part 2. Explain why this process is more effective when a wind is blowing. So if we consider that this is the person's skin, and here are sweat. Some molecules has large energy and some have smaller energy. So the molecules that have large energy will evaporate and they escape from the surface. When there will be the wind blowing, then the wind will be blow all molecules away from the surface, so more molecules absorb energy and escape. So I write here, when more molecules escape, then there will be faster evaporation. So faster evaporation of sweat as wind blows fast moving molecules away. Question number 5, part A. Figure 5.1 shows a wave on a sea approaching a harbor. So here is the figure 5.1, and in this figure there is a slit separation and wave is coming from right to left and it is approaching the harbor. Part 1. On figure 5.1, draw 3 crusts in the harbor. So here we have to draw the 3 crusts. So we can see in this figure that wave is moving from right to left and it is approaching the harbor walls. So there is a gap between these walls, and we know that when the wave passing through this gap there will be the diffraction. Now we have to draw the 3 crusts. These crusts will not be straight but they should be circular. So when I draw them, it will be, this is first crust and this is second crust, this is third crust. We know that the wavelength is the distance between two consecutive crusts are trough. So first of all we have to find out this distance, that is equal to lambda, one wavelength. We should have to be careful that the distance between all of these crusts should be equal to lambda. So these are the 3 crusts in the harbor. Part 2. Another harbor has a much wider gap between its wall. So there is another harbor whose gap is wider. Describe and explain how the pattern of wave crust in this harbor is different from the pattern you have drawn in part 1. So when the gap is larger than the wavelength, then what will happen? First of all, I write that when the gap is equal to wavelength, then there will be most diffraction. Secondly, when gap is much larger than the wavelength of incident wave, then there will be less diffraction or no diffraction. Third case is that when a gap is much smaller than the wavelength of the incident light, then most of the wave refracted back. So in this question, wider gap means that the gap is larger, and when the gap is larger as compared to wavelength, then there will be less diffraction or no diffraction. So I write here waves pass through gap remains straight. They don't bend in the form of circle, or there will be no diffraction. In the explanation, I write that less diffraction occur or there will be no diffraction. Next part B. A sound wave of frequency 850 Hz travels through sea water. The speed of sound in sea water is 1500 meter per second. Calculate the wavelength of the sound wave in sea water. Here we have to calculate the wavelength when speed and frequency is given. So by using relation that V is equal to F lambda, here speed is given and frequency also given, we have to calculate wavelength. It will be V over F. So speed is 1500 and frequency is 850 Hz. Wavelength comes to be 1.8 meter. So I write here wavelength is equal to 1.8 meter. Question number 6, part A. Figure 6.1 is a full-scale diagram of a lens and object O. Here is a figure 6.1 and object O is mentioned and there is a lens. Part A. The focal length of the lens is 3.5 cm. On figure 6.1, mark and label with letter F the positions of the two principal focuses. So on figure 6.1 we have to mention the positions of principal focus and focal length is given, that is 3.5 cm. So first of all we have to know about what is focal length. Focal length is a distance from the center of lens to the principal focus. So here focal length is given, which is 3.5 cm. Using this focal length we can easily find out the location of principal focus. So first I use the ruler and measure 3.5 cm on both sides of this lens. So when I measure it, it is at this position and on left side it is at this position. So these two are at distance 3.5 cm and these are the principal focus F. Part B. On figure 6.1, draw 3 rays to locate the image. Draw an arrow to represent the image and label the image with I. Now we have to locate the position of image. For that we use three rays. First ray is that, first of all, this ray passes through the focus point, and then this becomes parallel to principal axis. Second ray is that passing through the center of this lens and goes straight. While third ray, that first it is parallel to the principal axis and then reflection by the lens passing through the principal focus. Now I am going to draw the first ray that passing through the focus point. And then by our reflection by this lens, it becomes parallel to principal axis. So this is the first ray. Second ray passes through the center of this lens and goes straight. Third ray is that, first of all, it is parallel to the principal axis. And then by refraction by this lens, it passes through the focus point. The point where these rays meet is the image, and I label it with I. So this is image. We can see that this image is inverted, real, and it is in larger size as compared to object. So part C, state three properties of the image I. So this image is real, because this image is formed by the rays, not by backward extended of these rays. Second, it is inverted, because the object is upward and the image is in downward side. And enlarged. This means that the size of image is larger as compared to the size of object. Part D. A student incorrectly states that this lens is being used as a magnifying glass. So this lens is used as a magnifying glass, one student said. Part 1. State how the image produced by a magnifying glass is different from the image I. So first of all, we have to know that which image is formed by the magnifying glass. So magnifying glass makes upright and virtual image. But by this lens, the image is real, inverted. So both of these, magnifying glass and lens, differs by the image formation. So I write here image produced by magnifying glass is upright and virtual. Part 2. The student moves the object O to the position P so that the lens shows in figure 6.1 act as a magnifying glass. On figure 6.1, mark a possible position for P. So we have to locate the position of object, that is O, for the magnifying glass. We know that the magnifying glass produces upright and virtual image. For that, object will lie between F, that is focus point, and center of lens. So the object is between focus point and lens. So it lies from that point to that point. So I am going to locate this image, this object. So the object will be at this position. This is O and this position is basically P. So we have locate the object for magnifying glass so that upright and virtual image is formed by this. Question number 7, part A. Define electromotive force EMF. So here we have to write the definition of EMF. It is the energy supplied to the charges to move across the whole circuit is known as EMF. Energy supplied over charges. So I write here energy required to drive one coulomb charge around a complete circuit. Part B. Figure 7.1 shows a circuit. The two lamps are identical. Each lamp has a potential difference of 3.0 volt across it and a current of 2.0 ampere in it. PQ is the length of uranium metal wire. The resistance of PQ is R. Part 1. Calculate the value of R. Here we are given that the potential drop across both of these lamps is 3 volt. It means that 3 volt potential across this and 3 volt potential drop across this lamp. Second, the current through both of them is 2.0 ampere and also there is 2.0 ampere. And it is also given that the EMF is 12 volt. We have to calculate the resistance of this wire, PQ. So first of all, we can see here that both of these lamps are parallel combination, and in parallel combination, potential difference remains same but current changes. I write here parallel combination and series combination. Here I write potential difference and its current. In a parallel combination, potential difference remains same while current changes. It is different. The potential difference across the series circuit is different, but current remains same. So in this circuit we can see that both of these lamps are in parallel. It means that the potential difference remains same. There is a 3 volt potential difference across first lamp, and also in a second lamp there is 3 volt potential difference. And when we see the current values, the current in parallel combination is different. It means that total current is obtained by adding all currents. Here it is I1 and it is I2. I add and it comes to be 4.0 amperes. It means that total 4 ampere current passing through the circuit. So we also have to find out the potential drop across PQ. For that we can see that when I combine these two lamps, then the combination of these parallel lamps will be in series with PQ wire, and in series the potential difference is different while the current remains same. Using this idea, I have to find out the value of potential difference and the total potential, that is EMF of battery. It will be equal to potential drop across PQ plus the potential of lamp. By using this equation, we can find out the potential drop across PQ, and it will be equal to VPQ. EMF is given 12 volt and the potential drop across lamp is 3 volt. So it comes to be 9 volt. So here V is 9 volt and current through the whole circuit is 4 ampere. Because the whole circuit is in series, that's why in series circuit current remains same. By using these two values, I can find the resistance by using Ohm law. V is equal to IR and R is equal to V over I. Potential is 9 volt and current is 4. So the resistance comes to be 2.2 ohms. So the resistance of wire is equal to 2.2 ohms. I write here Part 2. Another piece of wire is made of the same metal as PQ. The length of the new piece of wire is twice the length of PQ. The diameter of the new piece of wire is twice the diameter of PQ. So here length is also double and diameter is also twice. Calculate the resistance of new piece of wire. Here we have to calculate the new resistance. So we know that resistance is directly proportional to length and it is inversely proportional to area. By combining these two equations, I can write R is directly proportional to L over A. So to eliminate this constant, that is proportionality sign, R is equal to rho, that is resistivity, L over A. As in the question, it is given that the piece of wire is same. So the resistivity remains same, it is constant. And the length is double, diameter also double. We can write this formula in terms of diameter. And area is pi r square. And we know that D, which is diameter, it is equal to 2r. Double the radius becomes diameter. Here we have to put the value of r. It will be equal to D over 2 square. And it is 4 rho L over pi D square. So this is basically the formula of resistance. And this resistance that we already calculate, it is equal to 2.2 ohms. But now the values are changed, that the length and diameter double. So I write here R is equal to 4 rho L prime, that is new length, and pi d square with prime. L prime is equal to 2L and d prime is equal to 2d. 4 rho 2L over pi 2d square, and it comes to be 2 pi 4 rho L over pi d square. This term is basically equal to the resistance and its value is 2.2. I write here 1 over 2, this is 1 and 2, and it is equal to R. This is new resistance. By putting the value of R, it is 2.2 and the new resistance comes to be 1.1 ohms. So the resistance is 1.1 ohms. Question number 8, part A. State the difference between an analog signal and a digital signal. You may draw a diagram to help explain your answer. So here we have to differentiate between the analog signal and a digital signal. So analog signal have any values, but the digital signal has two fixed values, 1 and 0. When I have to draw the diagram of digital signal and analog signal, so first of all I use the ruler. So the analog signal will be, it has any value, but the digital signal has two fixed values. It is 0 and 1. Again 0 and 1. So it's digital signal. And this is analog signal. I write here digital signal have only two states, that is 1 and 0, while analog signal can have any value. This signal has no fixed value. Part B. Draw the symbol for a NOR gate. Here we have to draw the symbol for NOR gate, and NOR gate is the combination of OR plus NOT gate. First of all, OR gate has two inputs and a single output, and NOT gate convert 1 into 0 and 0 into 1. It means that it performs the operation of inversion. When I have to draw its symbol, it will be just like this. So it has a single output while two inputs. This is OR gate. But when we have to apply NOT gate over it, we just place a bubble sign here and then we take output. So here if I consider that this is A input and it is B, so the output will be X and it is equal to A, R, B, and I have to apply NOT over it. Part C. Figure 8.1 shows a combination of logic gates X, Y and Z. The gates are not represented by the standard symbols. Here are three inputs A, B and C. By combining A and B, we get output D. And we don't know that which gate we have to apply here. Now by combining D and C, these are two inputs and then we get output E. And we also don't know that which gate we have applied there. No, E is input, but there is output C. Table 8.1 shows a partly completed truth table for this combination of logic gates. So here is the truth table. There are three inputs A, B and C and the outputs are D, E and F. So there are different combinations of inputs. Part 1. From table 8.1, deduce the name of logic gate X. We have to tell the name of logic gate in X. So first of all, we can see here that this is a logic gate X and it is formed by A and B. So going on the truth table, we see different combinations of A and B. Here we can see that here is 0 and 0. It gives D output as you can see from here. So this output is 0. The second combination is input 0 and 1. The output is again 0. Third combination is 1 and 0. The output is 0. And fourth combination is 1 and 1. The output is 1. We can see from here that when both inputs are high, the output will be high. But if any one of the input is low, output is also low. So first of all, this is a truth table for AND gate. I will draw it. I just consider that there are two inputs, not three inputs. So if I consider that it is input A and B, when both of inputs are low, 0, 1, 1, 0 and 1, 1. When I apply AND gate, then it will be 0, 0, 0, 1. We compare this table with the inputs A and B and output D. We can see that both of these are similar. So the gate that is at the place of X is actually AND gate. I write here it's AND gate. Part 2. The name of logic gate Y. So here we have to tell the name of the logic gate Y, that is here. It is formed by input C and D and the output is E. So we can see the truth table that it is formed by C and D and its output is E. So we check different combinations of input. First of all, input is 0, 0, output is also 0. Again, input is 1 and 0, output is 1. And then input is 1, 1, output is 1. And from this we can see that if any one of the input is high, as in this case and in this case, the output is high. And when both of the inputs are low, output is low. And when I write the truth table for OR gate, this 0, 0 gives 0, 1, 1 and 1. We compare this table with C and D and E. Then we can see that this gate is basically OR gate. I write here OR gate. Part 2. Logic gate C is a NAND gate. Complete column F of the table 8.1. Here C is a NAND gate. We can see from here that this is the logic gate C and it is NAND gate. NAND gate is formed by the combination of AND and NOT gate. And here is a single input E which is divided into 2. It means that we can see from E, it's a single input. If I consider that this is 0, then this input will be 0, 0. And if I consider E to be 1, then the input will be 1, 1. So when I write the truth table for NAND gate, it will be A and B and then I apply NOT over it. So 0 becomes 1 and 1 becomes 0. Here it's 1 and it is 0, it is also 1. So we have to fill the table according to this. When input is 0, 0, we can see inputs are 0 and 0, output is 1. So I write in first column output is 1. So when again the inputs is 0 and 0, output is 1. Second case is when inputs are 1, 1, then output will be 0. So I write here 0. It simply means that when both of the inputs are 0, the output is 1, and when both inputs are 1, the output is 0. So this will be 0, 1, 1, 0 and 0. So we have complete this truth table. That is the output of this circuit. Question number 9, part A. An X-ray machine requires a supply of 110 kilovolt. The mains electricity supply is 230 volt. A transformer is used to supply the correct voltage to the X-ray machine. There are 50 turns on the primary coil of the transformer. Calculate the number of turns on the secondary coil. Here we have to calculate the number of turns in the secondary coil when the number of turns of primary and the potential of primary and secondary coil is given. So the main electricity supply is 230, which is the primary voltage, and the X-ray machine requires a supply of 110 kilovolt, which is the secondary voltage. These are the number of turns of primary. We have to calculate the number of turns of secondary coil. For that we know that ratio of number of turns of primary to secondary will be equal to the potential difference of primary to secondary. I write here Ns over Np. It is equal to Vs over Vp. So here we have to calculate the value of Ns. Ns will be equal to Vs multiplied by Np divided by Vp. So the secondary voltage is 110 kilovolt, that is 110 multiplied by 10 to the power 3, and number of turns of primary is 50 divided by 230, that is the potential of primary coil, and the number of turns comes to be 24,000. So these are the number of turns of secondary coil. We can compare the number of turns that primary has 50 turns and secondary coil has 24,000 number of turns. It means that NP is less than NS. And we can also compare the potential difference, that VP potential difference is less than Vs. So we can see that this transformer is basically step-up transformer that increases the potential of secondary, or the number of turns in secondary are larger as compared to number of turns in primary. Part B. Draw a labeled diagram of step-down transformer. Here we have to draw the diagram for step-down transformer. In a step-down transformer, the number of turns in secondary is less as compared to number of turns in primary. On the label, state a suitable material for each of the components. So first of all, transformer consists of soft iron core and there are two coils, primary and secondary. So first of all, I draw the soft iron core. So this is the soft iron core and there are two coils in a transformer, that is primary and secondary coil. Here we have to make the step down transformer. It means that the number of turns of primary must be greater than the number of turns of secondary. So when I draw the primary coil, this is the primary coil, while the secondary coil has less turns, so it will be just like this. I label it as secondary coil. It's the primary coil. Or copper coil. And this is soft iron core. Part C. Explain how a transformer operates. So in this figure we can see that there are two coils, one is primary and second is secondary. When we apply the alternating current to the primary coil, then there will be the generation of alternating magnetic field in the primary coil, and this coil is magnetically linked with the secondary coil. As a result, there will be induced EMF in the secondary coil. So I write here alternating voltage R AC current in the primary coil produce an alternating magnetic field in the iron core. Which result an induced voltage which is also be called EMF at the secondary coil. So in this way transformer operates. Question number 10, part A. Figure 10.1 shows the beam of radiation in a vacuum. The beam contains alpha particles, beta particles and gamma rays. The beam enters a region where there is a strong uniform magnetic field. The direction of the magnetic field is out of the page. On figure 10.1, mark and label the path through the magnetic field of part 1 alpha particles, label this with alpha. Part 2 beta particles, label this path beta. Third one is gamma rays and label this path gamma. So here we can see that in figure 10.1, the beam of radiation contains alpha, beta and gamma rays. And the region of uniform magnetic field out of page, it means that the magnetic field direction is out of page. We represent this with dot. And the beam of radiation coming from left to right. So by using Fleming left hand rule, we can find out the direction of force. We use our left hand rule in such a way that second finger, third finger and thumb are mutually perpendicular to each other, and then if my thumb points in the direction of force, then the second finger is in the direction of magnetic field and third finger is in the direction of flow of these particles. That is, if I consider alpha particles, these are moving from left to right. So the direction of flow, it means towards right. And the magnetic field is out of page. Now I am using my left hand in such a way that the thumb points in the direction of force. If my second finger is in the direction of magnetic field and the third finger in the direction of flow of charges, that are alpha, beta and gamma rays. So when I arrange my left hand in such a way, then the point out the direction of force, and the force on the alpha particle will be in downward direction. And when I draw inside this, the bending of alpha particles will be in downward direction. So first of all, I draw this ray, that is central ray, the path of incoming ray. Now the alpha particle will be deflected downward direction. So this is for alpha particles. Second, if I consider beta, we know that beta particles are negatively charged. So their deflection will be in opposite direction as that of alpha particles. So they will be deflected in upward direction and they will be just like this. Second, gamma rays are neutral. They do not have any charge. So they will go straight. This is the direction of gamma rays. So part B, radioactive sources have many use in medicine. State 2 safely precautions which hospital staff take when working with gamma ray source. We know that gamma rays have large of penetration. Their penetration power is very large as compared to alpha and beta. So one has to take some precautions while dealing with gamma ray source. So first of all we have to limit the exposure time. I write here limit exposure time. And second one is that stand as far away as possible from the gamma ray source. Stand as far away as possible from gamma ray source. Next part C. Our radioactive isotope iodine-131 is used as a tracer in medical diagnosis. A nucleus of iodine-131 contains 53 protons and 78 neutrons. The symbol for iodine is I. Part 1. Use nuclide notation to show this isotope of iodine. So the symbol of iodine is I, and we have to write its atomic number and atomic mass. It's given that iodine consists of 53 protons. It means that 53 is the atomic number because atomic number is the number of protons present inside the nucleus. That's why the atomic number that is equal to number of protons, it is equal to 53. Next we have to calculate the mass number of iodine. Mass number is represented by A and it is the sum of number of protons plus neutrons. Number of protons are 53 and neutrons are 78. So the atomic mass comes to be 131. When I write here, so I write 131 and number of protons are 53. Part 2. Iodine-131 emits gamma radiations. It has a half-life of 8 hours. Explain why this emission and this half-life make iodine-131 a suitable material for tracer in medical diagnosis. So its half-life is given that is 8 hours and it is very useful material for a tracer in medical diagnosis. So first of all, I write here need long enough half-life. To be detected. Second is needs short enough half-life. To soon have very little activity. it means that it was not stay inside the body. And we know that the ionization power of gamma rays is very small as compared to alpha and beta. So I write here gamma weakly ionized or it can pass out of body without harm.